Well, welcome to our lesson on linear programming. This lesson is an extension of solving systems of inequalities, and our two learning targets include finding maximum and minimum values of a function over a region, and also solving real-world problems using linear programming. So we have been solving linear inequalities by graphing. And this included shading regions in the coordinate plane and finding the region that overlapped or intersected. In linear programming, we have a special name for this region, and this region is called the feasible region. The inequalities that we graph, those lines, whether they are dotted or solid, those are called our constraints. And the feasible region, sometimes it forms a polygon. And when that happens, when it forms a polygon, it is said to be bounded. It's a closed region that is bounded by each of those constraints. And if it doesn't have boundaries, if it's open on one side, it's said to be unbounded. So I've given you a couple of pictures here to clarify what those vocabulary words mean. So we will be using those kinds of words in this lesson. So sometimes in the real world, we want to maximize things such as profits or minimize things like cost or materials. And this can be modeled by a function. And in this lesson, we call that function an objective function. Those functions will be given to you. It's not something you have to develop. They will be given in the problem. What you will be doing is graphing the constraints, finding the feasible region, and then evaluating the objective function at the vertices of the feasible region to find out what the maximum and minimum values are if they exist. So let's start off with an example. In this example, we want to graph the system of inequalities over here on the left-hand side. We're going to find the coordinates of the vertices of the feasible region, and we'll find our maximum and minimum values of the objective function. The objective function is f of xy right here for the region. So we have three inequalities to graph. So that's our first task, is to go ahead and graph the inequalities. Well, x greater than or equal to 1. Remember, x equal 1 is a vertical line. Anything that's greater than 1 will be to the right of 1. Y greater than or equal to 0 is a horizontal line, and that turns out to just be the x-axis. And then this one, if you solve it for y, you get y is less than or equal to negative 2x plus 6. So 6 is the y-intercept and negative 2 is the slope. So go ahead and graph those three inequalities and you will end up with what I have graphed here in red. So the region we're talking about is the triangular region right here. If you take the intersection of all three of these constraints, you end up with this area right in the middle of this little triangle. So the next thing we need to do, we need to find the coordinates of the vertices of the feasible region. So our feasible region is this triangle. We want the coordinates of each of those vertices. Well, we can get those right from our graph. On this one, we have the coordinate 1, 0, 3, 0, and 1, 4. So our vertices are 1, 4, 1, 0, 3, 0. So we found that. The next task we have is to find any maximum or minimum values of the function. So what we're going to do is we're going to evaluate this function at each of these vertices. We're going to plug in this x-coordinate and this y-coordinate into the function f. So our first point is 1, 4. When we plug in a 1 for x and a 4 for y, we get 3 times 1 plus 4, which is 7. When we plug in 1, 0, f of 1, 0 gives us 3, and f of 3, 0 gives us 9. So the maximum value that we got was at 9, so that's our max value, and our minimum value is 3. Now, when we have a bounded region like this, we will always get a maximum and a minimum value. They will only occur at those vertices. If we have an unbounded region, we may not have a maximum or a minimum. That's something we'll have to look at. So here's another problem, another example. We're going to do the same exact thing. This time we have three lines, no verticals or horizontals. All of them have a slope. So the first thing you're going to want to do is put these in slope-intercept form so that they're easy for you to graph. And so I went ahead and did that. Solve each for y. So we can see we have two parallel lines. The green one and the red one are parallel. So, and then we also have another blue line that has a slope of 1/3. These two share the same y-intercept. They cross the y-axis at +3. So go ahead and graph those. This would be a good time for you to pause the video and see if you can successfully graph those on your own. I have done that for you. If you paused your video, here is what your graph should look like and your shaded regions. And I know my red line, the slope is off a little bit on that. It should be parallel to the green line. It needs to be slanted a little bit more on the bottom part toward the left. Our next task is to find those vertices. Well, in this problem, we only have 2 vertices. Okay, at the bottom, it's an unbounded region. It goes forever. So we only have 2 vertices to figure out. The first vertex is at 0, 3. We can get that from the graph. And the second vertex looks like it's at 1, 2, 3, 4. So those are our 2 vertices. So those are the 2 we want to evaluate the function for. And so I went ahead and did that. I plugged those into the function f using 0 for x, 3 for y, and then 3 for x and 4 for y. And I have these 2 values. Well, our maximum value is definitely 31 at the point 34. That's going to be a maximum. We're never going to get anything bigger than that. However, you can try to plug in some values in the shaded region here, and you'll find that there are values smaller than 12. So although 31 is our maximum, there does not exist a minimum value. An example I gave you here is the point 3, -2. If you plug in 3 for x, and -2 for y into our function f, we get a value that's less than 12. So we don't know what the minimum value is, so we just say that there is no minimum. So here's a real world example. Suppose you're screen printing t-shirts and sweatshirts, and we want to sell these as a fundraiser, and we have some constraints. We don't want to spend any more than 20 hours making shirts. We want to have no more than $600 for supplies, that's our budget. And we want to have at least 50 items to sell. So those 3 constraints. Some other constraints for our t-shirts, they take us 10 minutes to make those, each one. The supplies for each t-shirt is $4, and we make a profit of $6. For sweatshirts, they take 20 minutes, they cost $20, and they give us $20 in profit. So the question is, how many t-shirts and how many sweatshirts do we want to make to maximize our profit? And what is that maximum profit we can make with these constraints? So I went ahead and set up a table. This is a good idea for you. And I let x be the number of t-shirts and y be the number of sweatshirts. So x is t-shirts, y is sweatshirts. Now in red here, it says we want to have at least 50 items. So if we add those 2 together, we want to have greater than or equal to 50 items. So there's a constraint that we can graph. Then we have some things that deal with how much time it takes and how much cost there is to make them and how much profit we want to get. So the number of minutes for t-shirts is 10 minutes. So if we have x t-shirts, it's 10 times x. That's how much time it would take the t-shirts. If we had x t-shirts. If we have y sweatshirts, that would take us 20y as far as time. That's how many minutes it would take. And if we add that time together, we want that to be less than 20 hours. Well, now keep in mind these should be in minutes, so I need to convert my 20 hours to minutes, and that gives me 1200. So 10x plus 20y must be less than or equal to 1200. So that's another constraint. That's a line that we can graph. And our last constraint is the cost. The cost for the t-shirts are $6, cost for sweatshirts are $20. Multiplying that by the number of t-shirts and sweatshirts we make and adding those together, we can't spend more than $600. So that has to be less than or equal to 600. Our profit for each t-shirt, we make $6. For each sweatshirt, maybe we make $20. And we want that profit to be a maximum. So we want our objective function, our f of xy is 6x plus 20y. We want to find out where that function is a maximum. So I went ahead and put all of this information, here's all the information in the table. Now our constraints, one thing I need to mention, we have these top 3 inequalities are our constraints. We have our objective function, but there are 2 more constraints we need to think about. And those two constraints are, does it make sense to have a negative number of t-shirts or sweatshirts? And the answer is no. So we also have x is greater than or equal to 0 and y is greater than or equal to 0. We could have 0 of 1, so that 0 is a valid number, but that puts us in the first quadrant. So again, this would be a good time for you. I've already given you a graph here with some scales. See if you can go ahead and graph those 5 constraints and find the bounded region. All right, I have graphed those for you. Here is your feasible region, it is shaded in green here. And I've also labeled each of my constraints. All of them are solid lines because they can equal anything on there. And so now we have our region graph. The next thing to find are the coordinates of the vertices. Well, again, we have 1, 2, 3, 4 vertices that we want to find. And we just need to know which inequality we're using to figure out the value of the vertice, right? So this one down at the end, that one is 120, 0. This one right here comes from this inequality, so that's 50, 0. So those are 2 of our vertices. This vertex here and this vertex here are the other 2. So the thing we need to do is we need to solve this inequality, make it into an equation. So just make it 4x plus 20y equals 600. And solve that simultaneously with the one it intersects with, which is the one right above it. X plus y is equal to 50. So I would use substitution on that one. Say y equals 50 minus x, substitute it in for y and solve. And that will give you your x and your y variables, or the coordinates of that vertex. And that vertex turns out to be, I have it down here for you, it's 25, 25. So that's where those 2 intersect. And the last one is the intersection of 4x plus 20y is equal to 600. Intersecting with 10x plus 20y is 1200. And solving those 2 equations simultaneously gives us the point 100, 10. Now, if you're not sure how to get those points, be sure to ask me in class. That's basically using your substitution and elimination techniques that we learned in the section prior to this. So now that we have our vertices, we want to evaluate each of those vertices for our objective function f right here. And so I went ahead and did that. 120, 0 gives us a value of 720. 50, 0 gives us 300. 110 give us 800. And then 25, 25 gives us 650. So which one was the maximum value? Well, it looks like our maximum profit is $800, and it occurs when we make 100 t-shirts and 10 sweatshirts. So we need to make 100 t-shirts and 10 sweatshirts to give us a maximum profit of $800. Here's a lesson check for you. Now this one I'm going to have you work backwards. I want you to write the constraints that produce the feasible region that's shaded. I've already given you one of the constraints. I gave you y is greater than or equal to 0. That's this horizontal line. The other thing that you need to do is to be able to go ahead and find the other line. So for example, this is a constraint up here. Imagine that's a line up there, another horizontal line, and then you have this line, and you also have this line here. So I want you to find the equations of those 3 lines. Notice that they're dotted. So keep that in mind when you write your inequality. This one down here was solid, so keep that in mind. And so once you have those 3 constraints, find the vertices. You have 4 vertices that I want you to find the coordinates of, those 4 vertices. And then use this objective function with the 4 vertices you find to find your maximum and minimum values. And bring those answers to class. That's it for this video. See you next time.